Hello guys, welcome on Tesla Adventures. In this video, we'll discuss the Newton's law of cooling, which is a very important concept for heat transfer. And in this Newton's law of cooling, it states that if a body is cooling by radiating the heat energy, then what is the rate of cooling of that body? So we are only concerned in this topic about the cooling rate of cooling when body is cooling down just by emitting the radiations. Okay. So according to Newton's law of cooling, the rate of cooling of a body through radiation is directly proportional to the temperature difference of that body and its surroundings if that difference is very small. So the rate at which this body gets cooled, and the rate of cooling will be minus dt by dt, will be proportional to T minus T naught, where T is the instantaneous temperature of that body and T naught is the temperature of the surroundings. Greater is this difference between the temperature of body and surrounding, greater would be the rate of cooling. So let us prove this this law, and let us also conclude its final expression. So first of all, we know that, let us suppose that there is a body which is at a temperature of T and its surrounding is at a temperature of T naught. So the power emitted by this body will be sigma into one second. Yes. So the power emitted by this body will be sigma into E A T to the power 4, and power absorbed by this body is sigma A T naught to the power 4. We have already discussed in the previous video that the power emitted is this one and it depends on the temperature of the body, while power absorbed is this one and it depends on the temperature of the surroundings. So we have also discussed that for a single body, the emissivity and absorptivity are numerically equal. So we can write down the net power dq by dt as radiated power as sigma A T to the power 4 into E minus sigma A E T naught to the power 4. I am writing this A equal to E. So dq by dt will be equal to sigma EA, and this is T to the power 4 minus T naught to the power 4. Now we know that we have assumed that the emitted power is greater than the absorbed power, which means that we have assumed that the temperature of body is greater than the temperature of surrounding. So let us assume that the temperature of body is equal to T naught plus delta T, where delta T is the difference between the surrounding and the body temperature. So dq by dt will be equal to sigma EA, this is T naught plus delta T to the power 4 minus T naught to the power 4. Okay, now let us write it down again. dq by dt is equal to, this is sigma EA, this is T naught plus delta T to the power 4 minus T naught to the power 4. Okay. Now let us take this common and let us first of all write dq as ms delta T. Okay. And this ms delta T will be accompanied with a negative sign because the body is cooling down. So dt upon dt will be negative because as time is increasing, temperature is decreasing. So we can write down dq by dt as ms dt by dt. Now this is equal to sigma EA. Let us take T naught to the power 4 common, and this would be T naught 1. In fact, this would be 1 plus delta T by T naught to the power 4 minus 1. Okay, so this is minus dt by dt, and it would be equal to sigma EA T naught to the power 4 upon ms, and this would be 1 plus, in fact we will use binomial theorem, and we will use this 4 with delta t by t naught, like that, and I'm mentioning that using binomial expansion, because we have already assumed that delta t is very less than t naught, so we can use binomial theorem. So you can see that minus dt by dt is equal to sigma EA T naught cube upon ms into 4 delta t. So you can see this is rate of cooling, this is rate of cooling, and this is the temperature difference between body and surrounding, okay. And surroundings. So this proves the Newton's law of cooling, but we will do the further analysis on this. So first of all, let us assume this as some constant. Let us assume this as some constant c. So I can use this as c in further calculations. So minus dt by dt is equal to, this is c delta t, c, and this delta t is t minus t naught. Okay, so minus dt by t minus t naught is equal to c dt, and integrating both the sides, so you can see that this would be ln t minus t naught, and this would be minus ct. The limit would be 0 to t, and here the limit would be t initial to t final, where we are assuming that the initial temperature of the body was t initial, and at any time its temperature is t final. So this is the limit, t initial to t final, and this is ln t final minus t naught divided by t initial minus t naught, and it would be minus ct, and t final minus t naught is equal to t initial minus t naught into e to the power minus ct. So t final is equal to t naught plus t initial minus t naught into e to the power minus ct. This is the final expression of the temperature. And if we plot the graph between the temperature, final temperature, and the time, then you can see that this graph is an exponential decay graph. And at t is equal to 0, if we substitute t is equal to 0 here, then you can see the initial temperature was Ti, and the final temperature is Tf. And obviously we know that after infinite time, if we substitute t is equal to infinity here, so you can see that this would be 0 and t final would be t naught, and this is so obvious because finally the body will attain the temperature of the surroundings. So this graph would appear like that. Okay, so this is a exponential decay graph, and this is Newton's law of cooling. Now, in numerical problems, this formula is very hard to apply and very tough to remember. So I'll bring a very useful trick to solve the numericals for Newton's law of cooling, and it would give the result which is very accurate and very near to the result which we will obtain with this expression. So we can bypass using this expression, we can use that trick in numericals, and in next video I'll be bringing the numericals based on Newton's law of cooling. Now let us also discuss 3 limitations of Newton's law of cooling. The first limitation is the fact that this law is only valid when the difference between the body and the difference between the temperature of body and surrounding is very small, which we have used in binomial theorem here. Okay, the second is the fact that this law is only valid if the heat is being lost by a body by the method of radiation only. If that body is cooling down by some other method also, then this law is not valid. We are only concerned with the cooling of the body through radiations. And the third one is the fact that this law is only valid if the temperature of the surroundings is constant throughout. In the complete derivation, we have assumed T naught as constant. So this complete result and this derivation is only valid when the temperature of the surrounding is constant. So these are the three limitations of Newton's law of cooling. Thank you.